Today's speaker is Daesang Kim, who has been a postdoc for a few years now. Three years. He has been working on understanding reaction in porous media. The basic problem is when you understand reactions in a chemical lab, you do everything in a batch reactor, everything is well stirred and uniform and finely ground, and you get reaction rates. You take those same chemical species and you put them underground in a rock where you're flowing through pore structure, you get very different reaction rates. So that is what Daesang is going to talk about today. Daesang?
Thank you for the introduction. And thank you for coming. And yes, my name is Daesang Kim, and today's present title is the Upscaling Geochemical Reaction Rates Accompanying Acidic Carbon Dioxide Saturated Brine Injection into Sandstone Aquifers. This carbon dioxide is the primary greenhouse gas produced by the human activities, and the atmospheric concentration of carbon dioxide is increasing. So it has increased by 35% since the Industrial Revolution. And there's very simple stabilization wedge theory about the carbon dioxide problem. So the atmospheric carbon dioxide concentration is increasing, and if it is increasing at the current rate, they estimate it will be doubled in 50 years. So to stabilize this carbon dioxide concentration, we have to remove this triangle. And then they split, it's hard to see, but they split this triangle to 8 wedges, and then they remove each edge using a category of technologies. So they suggested this 8 categories of technologies. And there's a carbon capture and storage. Carbon capture and storage is a technology to prevent the carbon dioxide emission to atmosphere, and it can remove one wedge. And first, it captures carbon dioxide from large facilities, and then they sequestrate, they inject carbon dioxide in deep geological formations. And these saline formations, saline aquifers, are very strong candidates for the carbon dioxide storage because we have the large potential space for the storage, and we can find very easily. And for this carbon dioxide injection in saline aquifers, we have to understand the saline aquifers and this injection process. So saline aquifers are porous media, this porous media filled with brine, and this injection makes some reactive flows in porous media. So we have to understand the pore structures and reactive mineral distributions in these saline aquifers. So we need some numerical models for pore scale reactive flow simulation and upscaling of geochemical reactions. And these numerical models should have the advection and diffusion and chemical reactions for the reactive flow simulations. And there are a few of the numerical models for reactive flow simulation in porous media. And this Letts-Boltzmann method and the smooth particle hydrodynamics, they can simulate the reactive flows in porous media directly. But the porous media are so random and so complicated that so far they can work on these two-dimensional pore space. And the pore network model simplify pore space to a network of pores and channels. And this pore network model can simulate the reactive flows and upscale geochemical reactions to a larger scale. So for this study, we use this pore network model, and then a more realistic network model, we use the X-ray computed tomography of real rock samples. We have seen the overview, and next I'm going to talk about the network model construction and the reactive flow simulations in porous media. So for a realistic network model construction, So this X-ray computed tomography of real rock samples is used. And next step is the Postdoctoral network construction, and the mineral information is added to the network model for reactive flow simulations. And then this CO2 saturate brine injection in pore space is simulated. And for the simulation, we need the transport model and chemical reaction models. And using the simulation result, we upscale the geochemical reaction rates to a larger scale. And we'll see the conclusion. X-ray computed tomography of the rock samples is used to investigate three-dimensional microscale pore structures. And this is one example of the X-ray CT image. X-ray CT image consists of many voxels. A voxel is a cube, and its size about 4 micrometers. And then this is one slice of three-dimensional X-ray CT image. It has about 40 by 40 voxels. And then we take the many slices together, then we have the three-dimensional X-ray CT image. Reconstruction is the process to obtain the X-ray CT image. This is a cylindrical rock sample, and then X-ray is transmitted in this direction. Then we have this X-ray image. And then we produce this X-ray image at many different angles from 0 to 180 degrees. And we select this one row and then place the one row for all different angles from 0 to 180 degrees. Then we have this sinogram. And the process from this one row to this sinogram is called radon transform. This radon transform has its inverse transform, so we apply the inverse radon transform to this sinogram, then we have this reconstructed image. And then we apply this for all rows, then we have a three-dimensional volumetric image of three-dimensional X-ray CT image. And then here, the gray level, the gray color in this X-ray CT image represent how much X-ray is attenuated at each point. So that quantity is called the X-ray attenuation coefficient. So this X-ray CT image shows the X-ray attenuation coefficient in the rock sample. And for this study, the X-ray CT images of 3 Viking samples. The Viking samples are from the Viking Formation, Alberta, Canada, and they were imaged on the X2B beamline NSLS Brookhaven National Laboratory, and their resolution is 3.98 micrometer. And Viking 3W4 is a sandstone. It's their image size is 2.9 millimeter and 2.9 millimeter and 1.4 millimeter. Viking 10W4 is a shelly sandstone, and this is the image size. And Viking 14W5 is a conglomerate sandstone, and it has much larger grain size than the other 2 sandstones. And next step is the mineral identification. So this X-ray CT image is segmented into 4 phases: black, green, and gray, and red. Black phase is a void phase. And then gray phase is quartz. Quartz is the most common mineral in sandstones. So here in this image, about 80% and 90% is quartz. And then the green phase represents the minerals of that X-ray attenuation coefficient less than quartz. And then the red phase represents minerals X-ray attenuation coefficient greater than quartz. So here the dark grains are segmented to red phase. So we apply the 3 iterations of the biphase segmentation like this to have this 4-phase image. And there's a previous study about the Viking samples using a different techniques, the BSE and EDX analysis. This backscatter electron method is an electron microscope, so it can produce the 2-dimensional image of Viking sample surface, and this is a BSC image. And then this image is segmented to 4 phases. Similarly, the black, green, and gray, and red. And then this X-ray dispersive X-ray method, energy dispersive X-ray method, is applied to identify the mineral composition of each mineral phase. So the green is mostly kaolinite, which is a clay mineral, and gray is definitely quartz. And then the red phase contains the northite, calcite, and dolomite, and etc. And next step is the Postdoctoral network construction. This is one example of two-dimensional segmented image. So first step is to compute the meteor axis for the void space. So we compute the meteor axis using the thinning algorithm. Then we have these red curves. Then red curves represent the meteor axis. And then we compute a throat for each meteor axis path. The throat is the minimum cross-section along the meteor axis. So we compute throat for each meteor axis path. Then using this throat, we can partition this pore space to some pores. So in this case, this is one pore body, and this is one pore body, and one pore body. So we have 7 pores in this image. And this is a pore body from a real 3-dimensional X-ray CT image. So this transparent, the brown color represents the pore surface. And then the red voxels are the meteor axis voxels, and the white voxels are these throat voxels. And then after the Postdoctoral network construction, for each pore body, we compute the accessible mineral surface area of the green phase and red phase. And we use the marching cubes algorithm. And then the X-ray CT image has the microscale. So microscale is not enough for the mineral surface area. So we use this BET surface area to correct the microscale surface area. And then the corrected surface area added to the network model as reactive surface area. And this is the Postdoctoral network we have. And then using this Postdoctoral network, we simplified the pore space to a network of pores and channels. And then this simplified network has the network parameters of pore volume and pore surface area, and the channel length using the meter as path length, and channel cross-section shape and area, and pore-to-pore connectivity, and pore-to-channel connectivity. And then we add the accessible mineral surface area to this network like this, the surface area of the red phase and surface of the green phase. And then this network is going to be used for the reactive flow simulations. And this table shows the summary of the pore networks of the 3W4, 10W4, and 14W5. And porosity is the 14%, 4%, and 7%. And these are number of pores. And 14W5 has very small number of pores because it has large grains. Therefore, it has very large pores. So the number of pores is small. And these are number of channels. And the mineral volume of green phase is 15%, 10%, 3%, and red phase is this. And then the surface area of green phase is 60%, 65%, 48%. This value is very large when you compare it to this mineral volume of green phase. This because the green phase represents the clay minerals as came in the sandstone and covers the sand grains. So therefore, we have a large green phase surface area. And then these are red phase surface area.
This is the percentage of the total surface area?
Yes.
The total pore voids, the total pore surface area?
Yeah, total, yes.
And then the parameters that we were describing on the slide before, would that be a single parameter that's applied to all of the elements in the network, or would there be a range? So if you go one slide back,
Okay.
you have something like channel length and channel cross section, for instance. And when you look at the images below,
Yeah.
I can see that some channels look thicker and some channels look thinner.
Yeah.
So does that mean you would have a range of different values in your model,
yeah.
or would you apply a
So,
single parameter value to all of the channels within that model?
No, for the channel cross-section area, we use this throat shape and channel throat area.
Mm-hmm.
So this throat shape determines the channel cross-section, and the channel length is determined by this meteor axis path.
Right, so that might be different for different channels and different pores within the
Sure.
network.
Right.
Okay.
Every pore in the network corresponds to an actual pore in the...
So it's a real actual computational
One-to-one
reconstruction.
match.
Yep.
Right.
Yes.
Okay.
It's just we throw away small things like shape and...
Yeah, no, that makes sense. But that's good to realize that it's a really computational reconstruction of the real thing.
So is something flowing from one side of that diagram to another?
Yes. It's later it's used for the flow simulations. So if we inject some fluid in this direction, they can flow like this. So we use this simplified network to simulate that flows.
You'll probably get to that later, but I would think it matters where you inject the flow, right?
Yes.
Because,
Yes.
okay. So you'll probably get to that later.
Yeah. And the simulation problem is the carbon dioxide saturate brine injection in pore space. So the initially pore space is filled with brine with the pH 6.6 and the total dissolved solid is 0.45 molar. And then the injection fluid is the carbon dioxide saturated brine. It is on the 100 bar. Therefore, the carbon dioxide solubility is 1.0 molar. So some of this dissolved carbon dioxide changes to the carbonic acid. So this injection fluid is acidic. So pH is 3.1, and the total dissolved solid is this value. And the problem is simulated at 7 different injection rates. So the injection rate, the seepage velocity from the 0.058 centimeter per sec. That's the highest rate, and this is the minimum injection rate. And then this problem is simulated in the pore network models of 3W4 and 10W4 and 14W5. And this is the reactive transfer equation. This is the governing equation for the reactive flow simulations. So VI is the pore volume, and this bracket represents the concentration. So this is the mass change rate in a pore body. And this term is the mass transfer rate by advection. And this term is mass change rate by chemical reactions. And this term is the mass transfer rate by diffusion. So here the QI, QI is the volume flow rate through a channel. So this QI, this term is for the advection by the volume flow rate out of the pore, and this by the volume flow rate in the pore, and this chemical reaction term represented the chemical reaction with the minerals, and this is the diffusion coefficient multiply the concentration gradient. And in the advection term, we have the volume flow rate, Qij, from pore I to pore J through channel. So we use this simple equation. Qij is Cij multiply the pressure difference between two pores. And Cij is the channel conductance, and this is estimated using the channel cross-section shape and channel length. And then if we sum the old volume flow rate, then that should be 0 by the mass conservation. And then we replace this Qij by this equation, then we have one linear equation of unknown pore pressures. And then we apply this equation for all pores, and we have a system of the linear equation of unknown pore pressures. And we solve that linear system, then we can compute this PI, pore pressures, and we can compute this volume flow rate. And the chemical reaction model for this reactive flow simulation have two types of chemical reactions, the kinetic reactions and instantaneous reactions. Kinetic reactions, in the governing equation, we have this chemical reaction term. They are kinetic reactions. So they are mineral reactions with minerals. And for these kinetic reactions, we need the reaction rate and reactive surface area. And the other type is the instantaneous reaction. Instantaneous reactions have only the aqueous species. They don't have any the mineral species and mineral reactions. And we assume they are instantaneous. So they are always in equilibrium. So we need the equilibrium computation of instantaneous reactions. There are two kinetic reactions. The first kinetic reaction is on-site reaction. This is the chemical equation of the on-site reaction. This is the on-site mineral. And when it dissolves, it consumes the hydrogen ion and it produces this calcium, aluminum, and silicic acid. And then this is the reaction rate equation. In this equation, the braces represent the chemical activities. And chemical activity is computed using this activity coefficient and this concentration. And the activity coefficient is estimated using the Davis equation. And the KH to KOH are constants. And the omega, the saturation state omega, is defined like this. So this term is the equilibrium equation is divided by the equilibrium constant. So it equals 1. It means the reaction is in equilibrium. So there's no reaction rate. Omega is less than 1, then this reaction is dissolution in this direction. So, and the reaction rate is positive. And omega is greater than 1. This reaction is precipitation this direction. Precipitation, and the reaction rate is negative. And this reaction rate equation can be expressed like this, because this term depends on the pH, and this term depends on this omega A. And this is a plot of the R pH term and F omega term. So R pH term is large when the pH is low. So for acid condition, this R pH term is large. And this F omega term is bounded by 1 for dissolution. And this is the equilibrium state, and this is the dissolution region, and this is the precipitation region. So we don't have on-site precipitation, so I draw to this equilibrium condition. And the other kinetic reaction is kaolinite. This is a kaolinite mineral. So it dissolves consuming this hydrogen ion and releasing the aluminum and silicic acid. So the reaction rate equation is similar, so we can express R pH multiply F omega. And this omega is the saturation state for the kaolinite reaction. These are same. And this green curve represents the R pH term of the kaolinite. It's much smaller than R pH of the on-site. And then this green curve represents the F omega term of the kaolinite reaction. So for the dissolution, they are very close. And then for this region, the precipitation region. So for the precipitation, this equation, its magnitude increased too fast for the kaolinite precipitation. So we add, from a experimental study, we add 2 F omega models for the kaolinite precipitation. So one is the increase logarithmically, and then the other is magnitude is bounded by 1, like the dissolution. And for the kinetic reaction, we need the reactive surface area, here the AA and AK. So for the on-site reaction, we use the red phase surface area, and for the kaolinite, we use this green phase surface area as reactive surface areas. And these 9 chemical equations are instantaneous reactions. And instantaneous have the 9 reactions and only 15 aqueous species only. It doesn't have any mineral species. And we assume they are always in equilibrium. So we need to compute the equilibrium state of these 9 instantaneous reactions. So we use the Newton-Raphson method to compute the equilibrium state of these 9 instantaneous reactions. Using the simulation result, we compute the upscale reaction rate for the 2 kinetic reactions, ornithite and kaolinite. And the effective reaction rate is the net reaction rate from the Pore network simulation. So this is the sum of the all mass change rate by chemical reaction divided by the sum of the all the reactive surface area. So this is a weighted average. And we use another upscale reaction rate, RC, reaction rate from a quantum scale simulation. This quantum scale is much larger scale than Pore scale. So in this quantum scale simulation, the Pore network is just one grid. So the Pore network is just one grid with the total pore volume and total reactive surface area and total flow rate. So, and we can compute this reaction rate of the 2 kinetic reactions from this quantum scale simulation, and then this reaction rate do not have any Pore scale variation. So we can see this Pore scale variation by comparing these 2 reaction rates. And this is a simulation result of ornithite reaction. So this is time from 0 to 1,000 seconds. And this is the reaction rate. Solid line is from the Pore scale simulation, and dashed line is from the quantum scale simulation. They both increase and to go to a steady state. And this is the saturation state, omega, in pores. So this omega A is always very small. It's very small. It's less than 10 to the minus 10. So the ornithite reaction is always dissolution, and F omega is just 1. So the reaction rate equals to the RPH term, which is look like this. So this reaction rate is higher in more acidic condition. So we are injecting the acidic fluid, so pH decreases to a steady state, some acidic steady state. Therefore, this RA value increases to a steady state. And this ornithite reaction is always dissolution, so it consumes the hydrogen ion, and it produces the aluminum and silicic acid. And this is the simulation result of kaolinite reaction. They decreases to a steady state. And both these are reaction rate from the quantum scale simulation, so they have some difference. And this is the distribution of omega k in pores, and this is the omega equals 1, the equilibrium state. And this region is omega is less than 1, it's the dissolution pores, and this is the precipitation pores. So for the kaolinite reaction, we have kaolinite dissolution pores and kaolinite precipitation pores. And for this simulation, we use this F omega number 1 model, which is its magnitude increases very fast for the kaolinite precipitation. So therefore, the pores around here have very strong precipitation rate. So therefore, the pore scale simulation has very strong precipitation rate, and the quantum scale cannot have these pore scale variations. So its rate is its precipitation is much weaker than this pore scale simulation. And this omega k is increased by this aluminum and silicic acid from the ornithite dissolution. So omega k, here there's aluminum and silicic acid. So this omega k value increased by this ornithite dissolution. So this ornithite dissolution kind of induced the kaolinite precipitation. And we have the three models of kaolinite precipitation. It's F omega 1, 2, 3. And for the precipitation, this F omega 1, its magnitude is much larger than these two, and F omega 2 and F omega 3. Therefore, this is the kaolinite reaction. So this F omega 1 has very strong precipitation. And then this F omega number 2 and F omega number 3. F omega number 3 has very small precipitation rate. And this F omega number 1 increases too fast for a large omega k value. So this omega k distribution cannot have a large value. It cannot exceed these values. So usually this omega k distribution has a sharp peak around here. And F omega 2 and F omega 3 has kind of much smaller magnitude, so they can have a wider distribution. And this kaolinite precipitation produces, in this direction, produces this hydrogen ion. So this precipitation makes the fluid more acidic. So this ornithite reaction can have a stronger dissolution rate by this kaolinite precipitation. So for the using F omega number 1 model, makes a strong dissolution rate of ornithite reaction. And these three graphs shows the this seepage velocity dependence on this injection rate. These are the steady-state value of the upscale reaction rate, and this is the seepage velocity from the 10 to the minus 5 centimeter per sec, roughly 10 to the minus 2 centimeter per sec. And red color represent the ornithite reaction from the pore scale simulation, and green color represent the quantum scale simulation. So both have a very good agreement. And this ornithite reaction rate have these two, the seepage velocity and the reaction rate, have a linear relation, this log plot. So they have an exponential relation. So we can find these coefficients using the least square curve fitting. And then this blue color represents the upscaled, the kaolinite reaction rate from the pore scale simulation, and the black color is for the quantum scale simulation. So they are very close at very slow injection rate, and for larger injection rate they have some difference. It's because for a very small injection rate, this is the omega distribution, so every pore has the kaolinite precipitation, and then at this injection rate, there are some dissolution pores. And for high injection rate, there are more dissolution pores. Therefore, in this region, there's some large pore scale variation. So this quantum scale simulation cannot predict that pore scale variation, so there's some difference. And T99 is the time to reach steady state, and this is the V seepage velocity inverse. So this red color represents the time to reach steady state of the ornithite reaction from pore scale simulation. So for a small injection rate, we have the large time to reach steady state. So this ornithite reaction has a kind of a little proportional relation. And this green color represents from the quantum scale simulation. So this quantum scale simulation much smaller, the time to reach steady state. It's because the quantum scale has only one grid, everything is mixed, so it goes to steady state much quickly. And this is the T99 of the RNK, the kaolinite reaction from the pore scale simulation, and this is from the quantum scale simulation. So pore scale simulation have a much larger T99 than the quantum scale simulation. And in the governing equation, there's advection term and diffusion term and reaction term. So for each pore body, we can compute the magnitude of the advection term and diffusion term and reaction term, and we can compute the ratios, and we can make this plot for all pores. So x-axis is the log advection term over diffusion term, and y-axis log reaction term over diffusion term. And we have this plot. The red color represents the on-site dissolution, and green color represents the kaolinite dissolution, and blue color represents the kaolinite precipitation. So most points are in this region, the first quadrant. This first quadrant is where the advection is dominant. So in this problem, advection is dominant, and kaolinite precipitation pores have a little smaller advection term than this kaolinite dissolution pores. And this simulation is at the injection rate about 1/10 of this value. So there's more blue points, which means there's more kaolinite precipitation, and the points a little move up. And this simulation is the 1/10 injection rate of this. There's no dissolution pores. All pores have the kaolinite precipitation, and we have much larger. Not larger. It's the points are moves up, which means the reaction is relatively large than these two, and the points look like it's less scattered. But anyway, this region and this first quadrant are advection dominant regions. So this problem for all the injection rates is advection dominant problem. And it's a future study. So in this governing equation, this concentration and reaction rate of onorthite and kaolinite are only variables. The other parameters are fixed for the previous simulation, but this onorthite dissolution is roughly this value. So it takes about 4 hours to dissolve 1 voxel. So this 4 hours is within the simulation time, so we have to consider this onorthite dissolution effect on the pore space change and reactive surface area change. And the kaolinite reaction is very small, so we can ignore this kaolinite reaction. So this is one example pore space, example pore throat network. So there are 8 pores, and this white color represents the throats. So we have 8 channels, and we apply the uniform onorthite dissolution by 1 layer, then we have this image. We apply this 1 layer dissolution, so this pore has a larger pore volume, and then this throat is increased by about 1 voxel, and the onorthite surface area changes. And then we apply another layer dissolution, then we have this. We have a new throat because 2 pores touch it. And we apply another layer of dissolution, then we have this image, and we apply another layer until all is gone. So finally we have this image. So after each dissolution step for each pore body and each throat, we compute the variation of the pore volume and throat shape and throat area and reactive surface area. And then these variations should be considered for when we solve this governing equation. Then we have a new variables like the pore volume and channel cross-section area and the channel conductance and volume flow rate and reactive surface areas. And then we will have a very different simulation results, which are much more realistic. And finally, its conclusion. So we develop a method for mineral identification and mineral distribution in real porous rock. And we construct a pore network models of the real porous rock. So first we construct Postdoctoral network and compute the mineral surface areas, and then we add the transport model and chemical reaction model to the network model. And then we simulate the carbon dioxide saturated brine injection and upscale the reaction rates from pore scale to core scale. And we see the pH variation in on-site reaction, and we see the much larger pore scale variation in kaolinite reaction, and we see the dependence on the injection rates, and we see the 3F omega models for the kaolinite precipitation. It's all I prepared. Thank you.